Good morning, everyone. Sorry I'm a little late. So today we will continue to talk about supervised learning, and we'll talk about decision trees and random forest if we have time. Okay. All right, let's start with decision trees. So a decision tree is a tree-like flowchart that assigns class labels to individual observations. So it looks like a tree-like flowchart. And each branch of the tree separates the records in a dataset in increasingly pure subsets. So, for example, at one node, it will try to split the set here to two subsets such that the overall purity will be increased. For example, consider a tree with only two numeric feature variables, x1, x2. Let's see the following diagram. Suppose only two numeric variables. So here, all the training data sets, data points are here at root. And then the tree chose to use x1 to do the first split, and the threshold is t1. And if x1 is less than or equal to t1, go to the left branch, otherwise go to the right branch. And then here, the tree chose x2 to do the split, and the corresponding threshold is t2, some value for x1, x2. And then if it is less than or equal to t2, go to this region, otherwise go to that region. Okay. And on the right branch, similar things will happen, but it may choose to use different variables. Okay. So this is in general how a decision tree looks like. So from this diagram, you see that a decision tree at each node will only choose one variable to do the split. Okay, and also it will choose a threshold if it's a numerical variable. Okay. And also, variables can be used repeatedly. You see, x1 is used here and also here, and x2 is used here and also here. Okay. All right. So this is a result after the tree is constructed. Okay. The overall training data points are split to 5 regions corresponding to the 5 leaves here. Okay. So if I stop put them together, you can see that the first split is done using x1 with threshold t1. So the first split happens here. So this is the overall left branch, and this is the overall right branch. Okay. And at the left branch here, the tree uses T2 to do the split. If it's less than x2 to do the split. If x2 is smaller than T2, then R1. Otherwise, R2. So R1 and R2. But the overall goal is to increase the overall purity level of the observations. Okay, so let's see. How do we construct these trees? It uses a Hunt's algorithm. So let's see how this algorithm works. So let dt be the set of records that are associated with node t, and y be the class labels. Y only has 2 labels assumed. Okay. And step 1 is if all of the records in dt belong to the same class, so namely is completely pure, then t is a leaf node labeled at yt. For example, all of them have the same class, share the same class label 0. Then we can use 0 to label that node, node t. Step 2, if dt contains records that belong to more than one class, For example, 40% of 0, 60% of 1. Then partition records into at least 2 child nodes in such a way that the purity of the new sets of nodes exceeds some threshold. So if dt is not completely pure, okay, then split dt to 2 subnodes, 2 more nodes, so that the overall purity of these 2 subsets exceeds some threshold. All right. So far we talked about purity, impurity. So how to measure purity or impurity? We have 2 measurements. The first one is called Gini coefficient. The second one is called information gain. So take a look at the first one, Gini coefficient. Let's see the definition first. So Gini impurity is a measure of how often a randomly chosen element from the set would be incorrectly labeled if it was randomly labeled according to the distribution of the labels in the subset. So let's try to understand this definition. So first of all, it's a probability of incorrect assignment. So let's, in general, denote this in this way. Y hat is not equal to I given y is equal to I. So this is the probability of y is incorrectly assigned to a class, right? I can be from 1 to C. I has C classes. So it is kind of like expected value of this one. Expected probability of y is incorrectly assigned. So this expectation can be denoted as this. So it is a weighted average of this probability. And the weights are the class probabilities for each class. I is from 1 to C. Okay. All right. And then this is equal to this. This conditional probability is equal to this unconditional probability. That is because y hat is randomly predicted. That you see is in, it was randomly labeled. Okay, so y hat and y are independent. So that's why this conditional probability and this unconditional probability are equal. So that's why we can arrive at this stage, okay, this step. And furthermore, you see this p of y hat is not equal to I, is actually equal to p of y is not equal to I. That is because you see it is randomly labeled according to the distribution of the labels in the subset. So y hat has the same distribution with y. Y and y hat have the same distribution. That's why these two are equal. And if we let p of y equals I be denoted by p sub I, right, little p sub I, then we have this expression. Then we can distribute pi to the parentheses, right? And we have this, and summation of pi is equal to 1. So that's why in the end, we have this expression or formula for Gini. It's 1 minus summation pi squared. I is from 1 to C. Right? It's 1 minus summation of the class probabilities, square of class probabilities. Right? If there are only 2 classes, i.e. C is equal to 2, then we can write the formula, simplify the formula, and get an expression like this. So this is a quadratic function of P1, one of the probabilities, one of the class probabilities. So, and if we draw this curve, is a parabola facing down, somehow like this. It's x. This is fx. And this is 0, 1. It's symmetric symmetric about 0.5, and it's facing down because A is negative. And it achieves its maximum at 0.5. When P1 is equal to 0.5, this Gini is equal to 0.5. And we know that probability is only defined between 0 and 1, right? So technically, it's only defined in this on this region, okay, from 0 to 1. So this is how the Gini coefficient looks like when we have only two classes. And let's examine these three extreme cases. When P1 is equal to 0 or 1, the subset, the set is completely pure, right? They all belong to the same class. In that case, you see that Gini coefficient is equal to 0, in both cases, 0. On the other hand, when P1 is equal to 0.5, here, and you see that the Gini achieves its maximum at 0.5. So Gini is equal to 0.5. So apparently, Gini coefficient is a measure of impurity. When P1 is 0.5, that means the set is completely random, right? Sort of a complete chaos. When you randomly pick one element from the set, there is 50% of chance that is equal to 1 and 50% of 0. Okay, so it's completely random. Right? So in that case, Gini achieves its maximum at 0.5. Right? So overall, from this simple example, you know that Gini coefficient is a measure of impurity. Right? It's not a measure of purity. Right? So of course, at each node, the purpose of doing the split is to minimize the impurity of the subsets after the split. Okay. So, all right. Now let's move on to the second measure, entropy. Entropy is also called expected information gain of a random event. So before we talk about entropy, let's see how to measure information gain. Information gain is somehow like a measure of interestingness of some random event. So when something is very unlikely to happen, and if it does happen, we gain a lot of information. And if something will happen for sure, okay? And when it happens, we get no information. So it's totally it's not interesting at all. Even if it happens, even if it happens, okay, we get no information. Okay? So we need a function to measure the interestingness so that the following conditions are satisfied. So if the probability of the event is 1, it's completely predictable, then the function gives 0 if the event occurs. If the probability of the event is close to 0, so it's a very rare event, and then the function should give a very high value if it actually happens. And lastly, if the probability is 0.5, then it gives 1 bit of information if it happens. So this is kind of like the standard or unit for this kind of measure of interestingness. And turns out that this function, negative log 2 of p, satisfies all of these three conditions, right? Where p is the probability of the event occurs, right? So it's negative log 2 of p. So let's see a few examples. So first, how much information can we get from one fair coin flip? So if it's a fair coin, then is the probability of having a head is 0.5, and probability of having a tail is also 0.5. Okay. So let's focus on this event. Flip a head. Then if we get a head, how much information we can get? So it's log 2, log base 2 of p, and is negative log 2 of 0.5. 0.5 is equal to 2 to the negative 1, right? So if you take log base 2 of it, you get 1. Right? You get negative 1, right? And because we have a negative sign in front of it, so indeed, for this event, if we have a head, we get 1 bit of information. And secondly, let's see a very rare event. The meteor strikes the Earth. Suppose the probability is 2 to the negative 22. It's very close to 0. Right? Then if it does happen, then how much information we can get? Negative log 2 of 2 to the negative 2, so it's 22. Right? So the information we get is 22 times of the information we get if we get a head, if we flip a head. Right? So very big. And the other extreme case is a completely predictable event. For example, the sun will rise tomorrow. So this is an event that is almost completely predictable. Right? The probability is equal to 1. Right? Then in this case, if we apply this function, we get 0. So if you see tomorrow's sun, you get 0 information because it's almost completely predictable. Okay. So you see this function, negative log 2 of p, can be used to measure the interestingness of a random event if it occurs. Okay. All right. Now let's move on to entropy. Entropy is not the information gain of a random event. Is the expected value of the interestingness or information gain of a random event. So we need to consider 2 cases, both cases, it occurs and it does not occur, both cases. So on average, how much information we can get from a random event. Right? We need to consider 2 cases. So that's why it's expected value. Right? So it's E of IY. For example, let's consider Y. Y is a random event. We use the abstract version. Y can be equal to 0 or 1 with probability P and 1 minus P respectively. Then let's calculate the entropy of Y. So E of IY, and then expected value of a random quantity is just a weighted average of the values that it can take. Right? And the weights are the corresponding probabilities. So Y can be equal to 1 or 0, right? So the value, the information gain we can get if Y is equal to 0 is this, okay, is Y equals 1. And the corresponding probability is naturally this one. Similarly for Y equals 0 case. So these are 2. You can consider this is 1 random event or the outcomes of 2, if 1 random event or 2 random events. Right? Anyway, they are kind of like complementary events. Right? And then we can measure their information gain separately using their individual probabilities that it occurs. Right? And also the probabilities are P and 1 minus P. And then we can kind of summarize the result and get this formula. We know that A log B is equal to log B to the A. Log B to the A, right? And also we know that log A plus log B is equal to log A times B. So if we follow these 2 rules, we can have this formula. Negative log 2, P to the P times 1 minus P to the 1 minus P. So this is a formula for the entropy of an event with two classes, right? Two possible values, 0 and 1. And in general, if there are C classes, the entropy is negative summation pi times log 2 of pi. Or we can write it in this way. Same thing. Okay? In general, this is the entropy. So now let's see if the entropy is a measure of purity or impurity. I still consider actually, yeah, we won't prove it, but actually entropy is also a measure of impurity, measure of impurity. Let's see the relationship between entropy and Gini. So entropy is about 2 times of Gini if there are only two classes. So this blue curve is corresponding to entropy, and this green curve is corresponding to Gini. Okay. And if we multiply the Gini coefficient by 2, then you see the Gini and the entropy are very similar. They are very close. Okay. So this implies that if we have two class problems, then these two measures, because they differ very slightly, only slightly, they always choose the same split point. So, namely, they will, no matter you use Gini or entropy to construct a tree, you get the same tree, essentially almost the same tree. Okay. All right, so now let's see. In this session, we will discuss the following topics: how to train, visualize, and make predictions with decision trees. And secondly, how to regularize trees. And lastly, how to build regression trees. All right, let's move on. So first, train and visualize a tree. So we will use this decision tree classifier to build a tree for the iris data set. So we'll first consider classification problem. So we will import this class, decision tree classifier. So for illustration purpose, we will only use two variables in the iris data set, which are petal length and petal width. We just want to simplify the problem so that the tree we will build will be simpler and easier to examine and understand. So we will only use the last two columns in the feature matrix. We call it X, and the target is still the species of the flowers. Then we instantiate the decision tree. Notice that we set max depth equals 2. Okay? So this means the tree will have at most 2 layers. Okay? 2 layers means 2 layers of nodes, except for the root node. Okay? So for example, this is a tree with 2 layers. Okay? Layer 1, layer 2. Okay? All right. And then we fit the model on the entire data set. Right? And after the fitting process, it will print the class only. Right? And we can plot the tree using this plot tree function. It's very simple. Right? So this is how the tree looks like. Right? So see, there are some information. There is some information in each node, including the root node. So for example, let's examine this. So first, Gini. So this is a Gini for all of the training observations here. Is 0.007 at the beginning. And samples, this is the number of observations here in this set. And then value. So this gives you the counts for different classes. So at the beginning, 50 observations for for the first class, 50%, 50 observations for the second class and third class. Right? And then the first information, x1 is less than or equal to 0.8. So this is the how the split is done. It uses the first feature in X, which is petal length. I think petal length. If petal length is less than or equal to 0.8, go to the left. Otherwise, go to right. And take a look at this left leaf. So for example, here samples are 50, right? And if you check the value vector, all of the 50 observations are assigned to the first class. So that's why the Gini is 0. Right? Gini impurity is equal to 0 now. Okay. All right. So so basically that is what so this slide contains what I said, how to measure the Gini. So let's see how to calculate the Gini coefficient. We can, if we use a formula like 1 minus summation pi squared, is equal to 1, 2, 3. Okay. Let's calculate the depth one left node. 1 minus 50 over 50 squared minus 0 over 50 squared minus 0 over 50 squared. So exactly 1 minus 1, 0. So Gini is equal to 0. That's very clear, right? And then for depth 2 left node, the values vectors is 0, 49, and 5. If we calculate the Gini at this node is 1 minus 0 over 54 squared, 49 over 54 squared, 5 over 54 squared. So you get 0.168. So this is how to calculate Gini manually and verify the result. Of course, you can also use this formula to get exactly the same result. You can check all of the Gini impurity in each node, in other nodes. And notes, scikit-learn use the classification and regression tree algorithm, the CART algorithm, which produces only binary trees, which means non-leaf nodes always have 2 children. If you take a close look at the decision tree we just created, you see at each node, it will split the node to 2 subsets only. Although you know the y variable has 3 classes, it never splits a set into 3 subsets. It always splits a set to 2 subsets at most. It may end at a node, then the node will become a leaf. But if it splits, it only splits to at most 2 subsets. So that's why it's called a binary tree. This is called the CART algorithm. Then let's see how to do predictions. Suppose we have a new flower whose petals are 3 cm long and 2 cm wide. Then let's predict the species of this flower. So first, create this new observations data matrix. You notice that you need to make it a 2-dimensional object, right? 3 and 2. And then we use the predict function to do prediction. So the predict label is 2. So it should be the 3rd class, the last class. If we want to know exactly what kind of flower it is, right, we can pull out the target names. So it's Virginica, it's the 3rd type of flower. And we can, if we follow the tree, the rule of the tree, we can get the same conclusion. Okay, let's see how to follow the rule of the tree. So petal length is 3, petal width is 2. Right, so let's go back to our tree. So petal length is 3. So definitely x1 is greater than 0.8. So go to the right. And then petal length is also greater than 1.75, so go to here, right? So exactly, the class label should be 2. Right? So this is corresponding to the third class, 0, 1, 1, 4, 5. Oh, the label is not printed. Anyway. Yeah, in the notes, actually, there is another way to plot the tree. I think the node label is provided using that kind of way to create a tree. You can check your notes. All right, now let's move on to next part. Oh, yeah. So the tree can also predict class probabilities. So given the new observation, you can just call this predict proba function, and it will give you the probability that the new observation falls in each class. So apparently, the last class has the highest class probability, 97.8%. That's why the predicted value is 2, is label 2, last class. Of course, you can change criterion. So by default, the CART algorithm uses the Gini coefficient, but you can also choose to use entropy. And if we fit the tree again and plot it, you see that it's almost the same tree was constructed. Although now the measure of impurity is entropy now, it's not Gini. All right. Then let's move on to regularization. We know that whenever we build a machine learning model, we always try to find the optimal point that will balance the variance and bias, right? And decision trees is kind of like it's a model that is very easy to overfit your data. So without any restrictions, the tree will continue to grow until each leaf only contains one observation, so that the bias will be 0, right? So that's why at the beginning, we already set one hyperparameter max depth equals 2, right? So that we have a small tree, a neat looking tree. If we remove that, it will grow very big. So that's why we always need to regularize our tree. And this algorithm, let's see the CART algorithm again. Okay, so this algorithm works by first splitting the training set into 2 subsets using a single feature k and the threshold tk. If it's a numerical variable, okay, you have to choose a threshold. Okay. So the problem is how does this choose k and tk? So suppose we have a bunch of variables, right? How does the tree select a single feature variable and the corresponding threshold? The answer is it search for the pair k and tk such that the tree such that it will produce the purest subset after the split. So it will evaluate the overall impurity measure, for example, Gini or entropy, and try to choose k and tk such that the impurity measure is minimized. Okay, so it's an optimization problem at each node. Okay? And the cost function that the algorithm tries to minimize is this. The cost function is, for decision tree, is just a measure of impurity, either Gini or entropy. It's a weighted average of the left node and right node, right? And the weights are, count divided by the overall count, right? M left divided by M, so this is the weight for the left node, and M right divided by M is the weight for the right node. And M is the count for each node. Okay, once the CART algorithm has successfully split the training set into 2, it splits the subset using the same logic. and then the subset, and so on, recursively. So it will keep growing. Right? It stops recursing if it cannot find a split that will reduce the impurity, or it reaches a maximum depth. Right? So either it cannot reduce impurity anymore, or it reaches the maximum depth that we decide. And the decision tree makes very few assumptions about the training set. So if it is left unconstrained, the tree structure will adapt itself to train the data set and fitting it very closely, indeed, most likely to overfit it. So that's why we always need to regularize a decision tree. Right? Otherwise, it will grow forever. Right? To avoid overfit the training data, we need to restrict the decision tree's freedom during training. Okay. So we need to do regularization. So these are the hyperparameters that can be used to control the tree. So first, max depth, we have seen this. And second, min sample split. So this is the minimum number of samples a node must have before it can split. So it will control the growing, of course. Okay. And next one is min samples leaf. So this is the minimum number of leaves, samples a leaf node must have. For example, if it is equal to 5, then any leaf must have at least 5 observations. And then min weight fraction leaf. This is similar to the previous one. Just instead of using count, it uses a fraction, right? Or proportion. And next one, max leaf nodes, the maximum number of leaf nodes. So this is a hyperparameter that is difficult to control, actually. Before you construct a tree, it's hard to imagine how many leaves we need in the tree. So it's relatively difficult to control. Right? And next one is max features. So this is the maximum number of features that are evaluated for splitting at each node. Right? So this is an effective hyperparameter that can be used to control the overfitting of a tree. Right? So this is not. So usually, if we don't set it, it will use all of the variables in the features matrix to do each split. It will choose the best one among all the variables. Right? However, if you set it to be, for example, 3, okay, then at each node, it will randomly choose 3 variables first. And then among these 3, it will choose the best one to do the split. Okay. And last one is CCP alpha. So this is a complexity parameter used for minimum cost complexity tuning. The actual formula for this is unknown. It's kind of like a black box. But anyway, we can just understand it that it is a way to control the complexity of the tree. All right, now let's see. So in the previous example, we let max depth equals 2. Right? So now let's use another hyperparameter, mean weight fraction equals 0.2. So this means each leaf should have at least 20% of the training observations. Right? In our case, we have 150 observations, so 20% will be 30. Right? So each leaf must have at least 30 samples. So this is a restriction. If we apply that hyperparameter value, I call it tree 3 and fit it and plot it, is you actually get the same result. Right? Although we didn't restrict the depth of the tree, we still get the same tree. Okay, it's kind of like a coincidence. Anyway, and decision trees can also help us to figure out their feature importance. Decision tree can help us to figure out which variables are more important or which are less important. Because you see, when a decision tree is grown, at each node, it will choose the optimal variable to do the split. Okay. So consequently, some variables might be used repeatedly. Some variables may use less often. So this importance characteristic of a variable can be used to measure kind of the average importance of a variable. Right? Usually it is used, it calculates the mean decrease in Gini impurity for each variable. Right? So it will calculate, for example, x1, x2. Right? It's used like this. Right? For example, if our tree is grown like this, okay, at the beginning it uses x2. So how to measure the importance of x1? It will measure the decrease in Gini at this node, and also the decrease in Gini when we do split here, and take average. And then it will be the mean decrease in Gini for x1. Similarly for x2, it will measure the decrease in Gini at the root node and at this node, and then take average. All right, and then the results are calibrated so that the sum is equal to 1. The sum of the feature importances of all the variables is equal to 1 always. For example, let's see the feature importances for tree 3 for all of the 4 variables. So it turns out that 56% for petal length, 43.8% for petal width. And the first 2 features have 0 importance. So this is because actually, we only use 2 features, okay? We only use petal length and petal width. So of course, sepal length and sepal width have 0 importance. But anyway, the sum of them is always equal to 1. And yeah, we can compare them. Right? So third and fourth features. So next, out of sample accuracy. So the purpose of building a machine learning model is to do precise prediction for observations that it has never seen, right? So out of sample accuracy is the most important measure. So let's see. So previously, in previous examples, we didn't split data. So now let's split the data to a training set and test set and fit a decision tree just as before, okay, by setting only one hyperparameter value and then fit and score it. So the score is the accuracy. So apparently it's there is a big difference between the training set and the test set accuracies. All right. Then what if we use unrestricted model? So the training set can yield a 100% accuracy, and the test set has like 97.4% accuracy. Okay? Not bad. That is basically because the iris data set is very, very regular. Right? So even we don't do any restriction, we still have a very good accuracy on the test set. But pay attention to the 100% accuracy on the training set. Okay? So this is kind of an alarm of overfitting usually. And the feature importance. Oh, by the way, I reload the data in the previous one. You see, do it. Oh yeah. From here, I already reload the data. Okay, I ignored this fact, so that's why. Yeah, I see. So see, actually we reloaded the data. We use all features now from when we use this hyperparameter, mean width fraction, right, at this stage. We already reloaded data. And so this is wrong. I explained it wrong. So actually, the feature matrix has all of the features available, but even though you see, because our tree only used petal length and petal width, the first two variables have zero importance still. Right? Although they are in the feature matrix, they were not used. Right? And then, so now it makes sense. You see, so now let's see. The first two features have about 2% importance, right? And the third feature has the biggest, which is petal length, and petal width has the smallest, right? Yeah, that's why when I see this non-zero importance for the first two features, I was a little bit shocked because I thought only two features were loaded. But actually, we loaded four features in the second model, even the second tree model. All right, and then search for the optimal tree. Right? So we can tune the hyperparameters so that the out of sample prediction error is minimized. So that is usually the goal of tuning your model. So let's consider three hyperparameters: mean sample sleeve, max depth, and CCP alpha. We would use a grid search to find the optimal combinations of these three hyperparameters. Of course, you can choose to tune more, but it will take longer to do the tuning because grid search CV uses cross-validation to find the best model. In our case, you see we have so many three dimensions of hyperparameters, and for each dimension we have multiple values. So there will be a lot of trials in the cross-validation. Let's just call it classifier. I train a tree and set the parameter space and cross-validation and fit. And then we can get the optimal parameters. For example, CCP alpha is 0.01, and max depth is 4, and mean width fraction leaf is 0. It is 0. So these are the three parameters we tuned actually. So these are the optimal values. And then we can choose to refit our best model using the entire training set by ourselves. So how to pull out the best model? You can just use this dot syntax, dot best estimator, and then it will use all of the optimal values for the hyperparameters. And it is one of the models in classifier. And then we can call the score function to calculate the accuracy for the training set and test set. Right? So pretty good, pretty good. And remember this grid search CV class automatically refit an estimator using the best found parameters on the whole training set. So instead of doing it manually, defining the optimal model by ourselves, we can just directly call this classifier, right? And then, so this is automatically the optimal model, right? And then we can call the score, get the same result, right? Just for your information, right? You can choose to do this, right? To do it in this explicit way, or you can just directly use the classifier. It must be the optimal model. And then let's move on to our next topic, decision trees for regression. So sometimes the response variable is a numerical variable, right? In this case, it's a regression task. It turns out that decision trees can also be used for regression purpose. Let's simulate the data set by ourselves first. So we define a function which will generate the data for us. So if you look at this pattern, this data set, so this we have a single. Suppose we have a single y and a single x. Single x and single y. And if we take a closer look at the relationship, you can see that there is a very complicated relationship between x and y. Okay, so even if we fit a polynomial model, it's kind of very challenging, And in this, you can see this is kind of there are two types of patterns. Right? One is slow oscillation. One is fast oscillation, right? So overall, there is a underlying slow oscillation. So that is created using this function. Right? And the fast oscillation looks like this. Okay? It's created using this function. Okay. And then lastly, we add some noise, a noise term to each observation. That is our data. Let's try to use a decision tree to fit this data set. So we first consider two trees, right? One with max depth equals 3, one with max depth equals 6. And then that's directly fit the model. So see, we fit the model here already. We define the tree and fit the model on the entire data set. So tree reg 1, tree reg 2, corresponding to 3 layers and 6 layers trees. Then let's plot them. So this is just the tree with max depth 3. This is a tree with max depth 6. So apparently they are quite different. The first tree is overly simple. It cannot catch all of the patterns apparently, especially the middle part, right? And this max depth equals 6 is better, right? But hard to tell. Maybe it's overly complicated, right? And then let's plot the tree. Plot the first tree because it's easier to plot. It only has 3 layers. So if we plot this one, it will be very huge. The tree will be very huge. So take a look at this and try to understand how the tree is constructed. So first, there is only one variable anyway, so it's like so all of the splits are done corresponding to x. So if x is less than or equal to 7.286, go to left, otherwise go to right. So let's go take a look at the tree. So the first split occurs at here. Okay. Okay, if it's smaller than, go to left, and then go to right. Okay. Then take a look at here. If x is less than 2.06, go to left and then right. Okay. So let's take a look at here, 2 point something. So the second split happened here. So left, right. Okay. And then continue, go on. So from this tree, you see that so if max depth equals gray, then eventually we get 8 leaves. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8 leaves. And each leaf is corresponding to a small region. Right? For example, this is one region, and then so these are the 4 leaves on the left, and then the right leaves are quite. Some of the regions are very small, so these are corresponding to the right 4 regions, right? Or 4 leaves, right? And also from this plot, you see that the predicted value for each region is the average target value of the instances in that region. Right? So for example, in this big region, you see we have a horizontal line here. So this is the average value of all of the observations in this region. So it's y bar, y bar. So this is how the regression tree works. It splits the observations into regions, and then how to do prediction for observation in this region. Just take the average value of all of the observations, right? The y values in that leaf, the observation. So that's why you see so many like horizontal lines, right? And for max depth equals 6, so regions are smaller, so it will be it will be able to create this kind of curves, sort of like curves. But if you zoom in each region, you still use a horizontal line, right, to do the prediction, like some kind of y hat value. All right. Then let's see how the CART algorithm works for regression model. For classification models, at each node, it tries to minimize the overall impurity after the split. Right? How about for regression? It will try to minimize the mean square error, the overall mean square error after the split. Right? Where mean square error is defined in this way, is y, so it's the average of yi minus y bar square. Right? Why y bar? Because yi hat is equal to y bar within the node always, right? It uses the mean value. So y hat is equal to y bar in a regression tree. So that's why the mean square error had this kind of expression, right? So this is a mean square error at for each node. So it will try to minimize the weighted average of the mean square error of the left node and right node. So this is the overall loss function for a regression tree. It's very similar to the classification problems. Right? For classification, you minimize the weighted average of Gini or entropy. Right? So it's still an optimization problem. Just for now, the measure of the loss function is slightly different. Previously is impurity level. So now is mean square error. So of course we still want to minimize the mean square error. Right. All right. The decision trees are prone to overfitting again. So we can usually when we try to regularize the decision tree, we only need to regularize one hyperparameters because all of the hyperparameters are related somehow. Okay? You don't have to regularize all of them. For our problem, because we only have one x variable, we can just choose to optimize one. Some hyperparameters. Right? So before we do that, let's consider two cases. The first one is a model without any restriction. Okay, so it actually will interpolate all of the observations. So namely, it will grow the tree until each node, each leaf only has one observation. So that's why you see the trees completely kind of it's basically connect all of the points together to get a model, sort of a model. And the right one is the tree when we set mean samples leaf equals 10. It looks much better. Okay. Then let's see how to find the optimal decision tree. So this part is a measure of the decision tree without any restriction. Calculate the R square for this case, the left tree. Right? The R square for the training set is 1, okay, 100%. But the R square for the test set is only 82.25%. So this is clearly a sign of overfitting, right? Now let's see how to tune the tune the tree. Okay. Let's consider three hyperparameters again. CCP, max depth, and minimum samples leaf. And then we use research CV to use cross-validation to find the optimal combination of values. Then print out the result. So CCP is 0.01, and then so those variables we use. Okay, CCP max depth and mean samples leaf. Mean samples leaf is 2. Yeah. And okay, max depth is 10. It's quite huge. The tree, the optimal tree is actually very big. Okay. All right. Then let's calculate the R-square for the training set and the test set for the optimal model. So 92%, 84%. So there is still a very big difference between the two accuracies, right? Which means probably still there is a big sign that the optimal tree is still overfitting the data, right, somehow. So this is the unrestricted tree. This is the optimal tree. I think it looks pretty good. It looks pretty good. But although the R-square is still much smaller than the training R-square. And this summarize some the strengths, weakness, and parameters of decision tree. The advantages, the resulting model can easily be visualized and understood by non-experts. So this is very important. It's easy to communicate with your users, the customers of your model. And algorithms are completely invariant and scaling of data. So notice that we never scale the data, right, yet, because it's not necessary for decision trees. That is because you see at each node, it only chooses one variable to do the split. Right? So it's sort of like the features are kind of independent of each other. Right? It doesn't matter they have the same magnitude or not. So in particular, decision trees work well when you have features that are on completely different scales or a mix of binary and continuous features. So because you just don't need to pre-process the data at all. And the downside is it is easy to overfit your data. All right. Let's move on to the next session. We'll just quickly talk about random forests. Random forest is an extension of decision tree. It's a forest of decision trees. And because decision trees are very easy to overfit the data, we can extend decision trees to random forest so that it will overcome this overfitting problem. Right? So it's random forest is one ensemble modeling method. Okay? Ensemble means a collection of models. An ensemble is a collection of models. Right? And the random forest is a special case of ensemble methods because in this ensemble, all of the models are the same. They are essentially the same algorithm, although they may use different data sets. Okay. So let's see how to construct a random forest. Okay. So in the random forest, many decision trees are trained, but each tree only receives a bootstrapped sample of the observations. Okay. So basically, the first step is to do bootstrap. Okay. Sample rows from a training set with replacement. For example, suppose originally the training set has 100 observations. we will sample from the training set to create a bootstrap sample with 100 observations too. However, because we do the sampling with replacement, this bootstrap sample and the original training set are different, right? Are different somehow. Right? And then we build a tree on this bootstrap sample. Right? And we do it repeatedly. For example, I want to construct a random forest with 1,000 trees. Okay, then we will bootstrap 1,000 times. So totally we will have 1,000 bootstrap samples. Okay? And consequently, we will build 1,000 trees. Okay. So together, they are called a random forest. 1,000 decision trees. These decision trees are very similar. However, they are using different samples, different sets of data. And also, another difference between a tree in a random forest and an individual decision tree is that each node only considered a subset of features when determining the best split. Right? So this is another major difference. We know when we build a decision tree model, we can also specify max features, but it is usually not required. But in a random forest, and for each decision tree, right, only a subset of features will be used to do the split, to be considered to do the split. Right? So this is always true. So namely, the decision trees in a random forest are more random than a regular decision tree, right? Because there is an extra layer of randomness at each node, because we randomly select a subset of features to do the split. And later on, the forest of randomized decision trees votes to determine the predicted class. So for example, if we have 1,000 trees, given any new observation, it will do prediction using all of the trees. So you will have Y1 hat all the way to Y1000 hat. Okay. If it's a classification problem, then we will follow the majority rule. Okay? Find the mode of these Y hat values, find the most frequent class, okay? And that is the overall predicted value for the new observation. If it's a regression problem, just take average of these Y hats. That would be the predicted value. But let's see how to construct a random forest. It's quite simple. We will consider a classifier for now. Right? So import the random forest classifier, and then we still use the iris dataset. We load all of the X variables and split the data, build our first random forest. So n estimators, this is the number of trees in the forest. Let's use 100 first. And this n jobs allows for parallel computation and fit on the training set. And then quickly we can do prediction. Very similar way. First, specify the new observation, right? And then do prediction. Right? And we can also use other criterion, for example, entropy, to build a tree. Right? And we can get similar results. And most of the hyperparameters or in the random forest model are similar to the decision tree models. However, there are a few ones that are very important and special. The first one is max features. So this one determines the maximum number of features to be considered at each node. I think by default is, yeah, there are some default values. Right? And then bootstrap. So this bootstrap parameter allows us to set whether the subset of observations considered for a tree is created using sampling with replacement or not. By default is true. Bootstrap, this type of parameter by default is true because it will use Bootstrap. However, you also have the option to do sampling without replacement. Then in that case, you need to set the size of the sample. Right? It cannot be the same, cannot be equal to the original training data set, because otherwise the sample will be exactly the same with the training set. Then you cannot have a different tree on different set anymore. Right? So very rare. Usually we let it be true, but tomorrow, when we talk about other ensemble modeling methods, in general, we will consider the sampling without replacement case, right? Similar like a random forest, but not exactly a random forest anymore. And n estimators is the number of trees. Accuracy, we can call the score method. So you see, if we use a random forest without tuning the model at all, the accuracy is very high. Right? It's very high already. It's close to 100. So the training set has a 100% accuracy, and the test set has 97.4% accuracy. And it's also able to evaluate the feature importance. Right? So now it's more balanced because you see we have a collection of decision trees, right? And because of randomness for the decision trees in the random forest, you see higher importance for the first two features. Right? That is purely because random forests are kind of more random. Okay, the decision trees are more random. At each node, it will randomly select a subset of features usually, and then among them choose the best one. Right? For classification models, the default max feature is square root of p. For example, in the iris data set, p is equal to 4, right? 4 variables. So square root of 4 is 2. So at each node, it will randomly select 2 features to do the split. And among the 2, choose one, choose the optimal one to do the split, right? So that's why these 2 sometimes were randomly chosen to do the split at a certain node, and then among them choose one to do that with them. So that's why the importance of them are slightly higher than a single decision tree.